Hi everyone, welcome back. This is example 7-8 in our friction and inclined planes chapter. And even though there's no inclined plane here, there's certainly going to be a lot depending on friction. So let's go ahead and read this and try to make some sense of it. The two blocks with, by the way, I have this indicated as small m is a small block and uppercase M is a large block, with mass 16 kilograms and 88 kilograms respectively, shown in the picture, are not attached. The coefficient of static friction between the blocks is 0.38. That's our mu sub s. But the surface beneath the larger block is frictionless. Okay, so just pretend that's ice on the bottom or wheels or something virtually frictionless. The question is, what is the minimum magnitude of the horizontal force F required to keep the smaller block from slipping down the larger block? All right, so we're applying a force F to that whole system, and there's no friction between the large block and the floor or the ground, but something is keeping up the small mass m and preventing it from sliding down the larger block. All right, the question is, what is that something holding it up? Because there's nothing underneath it, but there is friction. And so we have static friction existing between the smaller block and the larger block, and that's our F sub s. All right, it's important to point out that there's no friction between the larger block and the ground. All right, so it's that smaller block that remains where it is because static friction force is holding it up. All right, so the question is, what is creating that static friction force, which is supporting the mass m, or our lowercase m? Okay, what is that? What is creating that static friction force right there? Well, we know by our definition of static friction force that static friction is the coefficient of static friction times the normal force, right? We know this from our notes. All right, well, what is that normal force? Oftentimes we think of a normal force as being something vertical or applied perpendicularly, which it is, but let's think about now, all right, the force in between these two blocks is acting perpendicularly in between their surfaces. And so that normal force is that force that acts between them. All right, that's the perpendicular force acting between the two surfaces. And in problems before that we've done like this, we've called that force between the two surfaces the contact force. And that's what we're going to call it. So our normal force acting between them is going to really be our contact force between small block and large block. All right, so that contact force, or normal force, is really working in conjunction with that coefficient of static friction to create the actual static friction force, F sub s. All right, so the static friction force is what's holding up small block m, but that is created by those two values working together. So here's our plan of action. All right, we want to determine, first of all, what the static friction force needs to be to support the small block. What that will do is it will help us to determine what the contact force needs to be between the blocks. All right, and that will determine what the total applied force to the entire system, capital F, needs to be. All right, so that's kind of our goal right here. So we're going to go from the small block and then look at the big block, and then look at the entire system. So let's go ahead and draw a small or a free body diagram for the small block. All right, we're going to sum up the forces on the small mass m right here. And for starters, we're going to sum up the forces only in the y direction. All right, why is that? Well, because we don't want the block to slide down. So we want to make it such that the forces are in place so that there is no movement in the y direction. All right, so what's the first force you're going to draw in? Well, most likely it's going to be the weight force, right? We call that mg, the mass of the small block times acceleration of gravity. But also acting in the y direction here on the small block, we certainly hope, is going to be that static friction force that is holding it up. And so, since we expect that block to not slide down, or we don't want it to slide down, we're going to say, all right, well, the net force in the y direction is going to be 0 newtons. And why can we say that? Well, because all forces in the y direction are balancing each other out. We want it to be such that the static friction force is equal and opposite to the weight force, so the block doesn't move at all. All right, so let's, what we have here is a net force statement in the y direction as kind of like a global statement, right, on the whole block. But now if we sum up our component forces, we can say the net force in the y direction is the static friction force acting upwards minus that weight force acting downwards. Both of those statements being true about net force for the small block, we can say, all right, let's just take them and set them equal to each other. So static friction force minus the weight force equals 0 because we don't want that thing to move at all. So there's no net force on that small block. All right, let's take a look at this now. The static friction force. I think we can write that in a little more detail, can't we? Isn't it true that the static friction force is the contact force, we also call it the normal force, times the coefficient of static friction, right? If that's the case, then we can take that and we can plug that right in there. All right, so we have a statement about the contact force now being part of the statement about the whole net force on that small block. So let's take that and put that in terms of the contact force. First of all, we don't care about that 0. We're going to move everything else over to that side. So we're going to add the weight force and we're going to divide by the coefficient of static friction right there. This is going to be important to us later on because that contact force, the force between the two blocks, is going to be important. So this is stated in such a way that the small block doesn't move down. All right, so we've got that in place. So what we're going to do is just put this off to the side, or I'm going to put it off to the side. You can probably do a dotted line box around that because it's going to be important later on. And now let's look at just the large mass only. The large mass. So draw a free body diagram for just the large mass. We're going to look at that only. So what's the only direction this is moving? Well, it's not excuse me, it's not rising up in the air, it's not sinking down into the surface, it's really only moving in the x direction. So let's sum up the forces for this mass in the x direction only. Well, what is the force acting on this mass? What force is making this mass move? Well, the only force that's acting on it is that contact force. Why is this moving at all? Well, because the smaller block that is suspended is pushing it. So it's the contact force from the small block that is really being applied to the large block that's causing it to move. All right. And yes, that's in the x direction. Sorry, that keeps blinking on and off. All right. So as far as component forces acting on the large block right here, we can make a statement about the net force on that large block. What's the net force? What is the only force? The only force acting on the large block is the contact force coming from the other block, from the smaller one. In fact, there's not even friction acting on this, right? Because we said at the very outset that there's no friction acting between this the large block and the surface. So this is true, that the contact force between the two blocks is the net force acting on the large block right here. All right, well, what else is true about the net force in the large block? Well, Newton's second law tells us that the mass of the large block times the acceleration of the large block is a statement about the net force as well. Okay? It's Newton's second law right there. That you might say that that's a global statement about the large block. All right, well, since we have two statements about the large block, for net force, that is, we can say we can set them equal to each other. And that's exactly what we're going to do. So we can say the contact force on between the two blocks equals the mass of the large block times acceleration of the large block. Okay, well, what can we do now? Well, remember before we set that statement about the contact force between the two blocks off to the side? Remember, the contact force really acts in pairs, and so the contact force acting on the small block and on the large block is essentially the same thing. It's sort of like an internal pair of forces. And so since we have two statements about the contact force, we can then set them equal to each other. Let's just bring that up and say, all right, the force required to keep the small block in place is also, is a contributor towards moving the large block right there. All right, so this is true. So where can we go from here? Well, the thing that links all parts of the system together is the acceleration of the system. So right now we have a statement involving the acceleration of a large block. So let's state everything in terms of the acceleration for the large block. Let's divide down that large mass m. And so now we have a statement about the acceleration of the large block. This is going to come in handy later on because we're going to kind of set it equal or relate it to the acceleration of the whole system. So let's take this now, and you'll probably dotted line box it, but I'm going to take it and put it off to the side and just kind of dim that a little bit. And now let's look at the entire system. Like I said before, we're going to look at the small block, the big block, and now the whole big picture, the entire system. Well, the net force on the whole system is the mass of the system times the acceleration of the system, right? Newton's second law. That's a global statement for the whole system. But also true in terms of component forces is that the net force on the system is really that applied force F that we're trying to solve for. So we can say that's the case as well. That being true, we can set them equal to each other and say that that applied force is going to be the mass of the system times the acceleration of the system. Well, what did we say before about acceleration? Well, the acceleration of the system is the same thing as the acceleration of all the parts of the system. Block 1, block 2, the whole thing. So, if we rearrange that for acceleration of the system, and we say, wait a minute, we have this down here, a statement about the acceleration of one part of the system, we can say, then those two statements must be equal to each other, right? Because acceleration of the system is the same thing as acceleration of the whole of any one part of the system. So we can just take that out and set those two sides equal to each other. That seems to clear things up a little bit, right? Remember, what are we solving for? We're solving for that required force F, that applied force on the outside of the whole system right there. So we only have one thing to do to really solve for that. Well, first of all, let's just, I'm going to clean things up and just get rid of everything else right here. This is our working equation to solve for that net force. So I'm going to multiply out my mass of the system right there. And that's going to be multiplied by the whole other side right there. So hence those extra brackets. And remember, the mass of the system is really mass of the large block plus mass of the small block. All that's left to do now, I believe, is just to plug in our knowns, because we know the mass of the two blocks. We know the coefficient of static friction. All that's left to do is, as we say, plug and chug and solve for that outside applied force. What is that going to be? Well, we've got our mass of the small block times acceleration of gravity. Divide that by the coefficient of static friction. And by the way, I'm going to do that in this order. I work from the inside of the parentheses toward the outside. So I'm going to multiply the two reds and divide by the yellow. And then I'm going to divide by our 88 kilograms. And then take that whole value and multiply it by the quantity 88 plus 16. So what do we get as our net force? I get 488 newtons. That's a little over 100 pounds, maybe about 125 pounds. All right. So you're going to have to apply quite a good deal of force to keep that 16 kilogram block from sliding down, so as to create enough friction to keep it from sliding down. So there you have it. That's our applied force that's required, and that's our answer. Thank you for following along. If you have any questions, please make sure you see me. In the meantime, thanks for watching. I'll see you on the next one.